This lesson is 1.2.9a, Gliders in Flight. So the big concept of this lesson is that you will learn about gliders, their flight patterns, and how they are controlled. So first, let's look at an example of a glider in flight. This is a glider. Gliders do not have motors. Gliders fly by being brought up into the air by other aircraft and then gently glide to the ground. No motor whatsoever. So gliders can actually travel a significantly long distance as long as they are straight and level. Straight and level gets them their maximum distance. And you can see in the top image that if we have a horizontal versus an angle flight path, obviously the hypotenuse of that angle is further than if it just went flat. So how do gliders gain altitude? Well, gliders don't have an engine and they use rising air to gain altitude. So as they are in the air, they move in a cylindrical type pattern to gain altitude. So they create lift using a unique wing format, which we're going to look at in a second. Now, just like any other aircraft, the glider is susceptible to the tree axis of movement. So all the forces of flight that we've discussed previously still apply to a glider. This includes any movement in yaw, any movement in roll, and any movement in pitch. In order for a glider to have static stability, we need to maintain equilibrium in flight. So as you know, that means there is a balance between weight and lift. This graphic here shows an equilibrium of flight as well as a statically unstable airplane. That means that it has equilibrium and then is disturbed for moments or has an increased disturbed condition and then becomes statically unstable in a divergent way. Then we have a neutral static stability where we have equilibrium and then we're disturbed, but we have no additional moment. So the airplane actually holds that disturbed condition. So this statically unstable divergent flight has continued movement. So that's the difference between a neutral static stability and a statically unstable airplane, or in this case, glider. Okay, now we can also have dynamic stability. This is where we can start with statically or dynamically stable. That means that we have equilibrium and then we have it's statically stable and then dynamically stable moments and then it returns to that state of equilibrium. So you can see in this image, the nose goes up and then we return down and back up. And so we're creating that up and down type pattern. The second graphic here shows a statically stable but neutrally dynamic stability. So again, we have equilibrium and then we have some movement in the pitch. Then our last one is that is statically stable but dynamically unstable. So the moment tends toward the equilibrium, but the oscillation is divergent. So it's pretty much all over the place. So in terms of lateral stability with the roll, a high wing aircraft are naturally stabilizing. A lot of gliders have a high wing, so that way they are naturally stable. And then they also tend to be a dihedral. So we have lateral stability using the dihedral, which means that we have a dihedral angle right here. That means the wing is not completely straight. It actually is tilted away from the fuselage. So why does a dihedral work? Well, that's because we have equal length of the lifting surfaces, and when it turns, one side actually becomes longer while the other becomes a little bit shorter in terms of creating lift. So when we're flying straight, the weight is in the center, and then we have uniform lift on both sides, as previously mentioned. And then when the component of weight causes a side slip, it is actually able to counterbalance itself. So here you can see if we have induced relative wind here, and then we have higher lift here, and then a lower angle of attack over here, what we're resulting in is a rolling in the moment. So our moment is about our center, and the glider is essentially compensating for that angle. So here we have different types of dihedral. So this is that high wing that is naturally stable that we discussed. So that's a no dihedral. Then we have a straight dihedral, which is just two angled pieces of wing, such as that. A tip dihedral, the center is actually pretty much a no dihedral, but then the tip is what creates the dihedral angle. And then the polyhedral, poorly demonstrated by the line drawing here, is where we have different parts at different angles actually, so they align differently. So the real trick here is to avoid stalling. We haven't really talked about stalling up to this point, but basically, if you get to a certain angle of attack, an effective angle attack, eventually you are going to get to a pocket of air where you actually lose lift, and that's known as the critical angle of attack. So when the nose of a glider or any aircraft hits that critical angle of attack, you have a stall. Now, typically you think that when an engine stalls, the engine cuts out. In this case, gliders do not have engines, so it's more like a temporary suspension and then a begin to drop. So weight and balance is super important with a glider, as it is with any aircraft. If we look at what we're seeing here, which is an example of a glider, you can see that the center of lift is right here. And then we have weight at the center of gravity, but we also have weight forward of that and back of that. This is balanced, but it's really easy to shift because it's very nose heavy and very tail heavy. So how do we know where to place the center of gravity? Well, we have to be really careful about where our wings get placed so that way we fall within the center of gravity range. So we have to fall within certain limits depending on the length of our fuselage. So all of that are things that you will look at in the simulation in class.